Welcome. In this session, we'll start our look at graphing with asymptotes. Intuitively, an asymptote is a tangent at infinity. Somewhat more precisely, an asymptote is a straight line, or just possibly a half line if it's on just one side, such that as you go further away from the center of the graph, so towards infinity in either direction along that straight line, then there are portions of the graph which are arbitrarily close to that straight line. For graphs of functions, we can make this more precise using limits. For functions, we have to distinguish vertical from non-vertical. A vertical asymptote is a vertical straight line x equals c, such that the function has infinite limit at c, or just on one side possibly. The reason is that if you take a point that's further out along a vertical straight line x equals c, that means we have a point with x-coordinate c and y-coordinate that's numerically large. If a point on the graph of the function is close to this, that means the x-coordinate should be close to c and the y-coordinate should be numerically large. So if this happens further and further out and the points are getting closer, it just means that x is getting closer to c and f of x is becoming numerically large, so it's going out towards infinity or negative infinity. For practical reasons, we will distinguish between horizontal and oblique asymptotes. We say that horizontal line y equals L is an asymptote to the graph of f if f of x has limit L either at infinity or negative infinity. So if you go towards the right end of horizontal line, that means x is going towards infinity, and if f of x is approaching the line y equals x, that means y coordinates are getting closer and closer to L. So y equals L touches the graph of f as you go further out to the right end, the same as saying that the limit at infinity of f of x is L. Same thing works for negative infinity. Of course, you take the limit at negative infinity. For slant asymptotes, we cannot talk about limits. We have to fall back on the definition. You have to look at the distance between the function and the slant straight line. Rather than to take the actual geometric distance, it's more convenient to look at the vertical distance. That is to say, difference between the y-coordinates. A slant straight line will have an equation of the form y equals mx plus b. Difference between the function and the slant straight line will be f of x minus the quantity mx plus b. So the slant straight line is an asymptote at the right end if this difference has limit 0 at infinity, on the left end if the difference has limit 0 at negative infinity. The difference between our definitions of horizontal and slant asymptotes is just for convenience. In some sense, our definition for horizontal asymptote is almost same as the definition for the slant asymptote, because if the limit of f of x is L, limit of f of x minus L should be 0, and also the converse is true. If the limit of f of x minus L is 0, the limit of f of x equals L. So how do we find asymptotes? We will limit ourselves to rational functions, where it's quite easy to do this, at least if they're in standard form and we are able to factor. To find vertical asymptotes, we just use our knowledge of limits of rational functions. If the rational function is defined, the limit is the value. If the rational function is not defined, we first reduce the fraction to its lowest terms, and if the function is still undefined, if the denominator is 0 at some number, then we know the original function has infinite limits. So this gives us a simple way of finding vertical asymptotes for rational functions, of course assuming that we can factor. Reduce the fraction representing function to its lowest terms and then find where the denominator is 0. You have to be careful because sometimes people say a rational function has vertical asymptotes where the denominator is 0. This is wrong unless you know that the fraction is in lowest terms. We know that if the fraction reduces and the reduced fraction is defined at some number, then the limit exists and is equal to a finite number, equal to the value of the reduced fraction. So always check to see if the fraction is reduced before you find asymptotes. For non-vertical asymptotes, again we can fall back on our knowledge of limits at infinity and negative infinity. We saw in section 10.2 that if the numerator has smaller degree, then the limit at infinity and negative infinity are both the same, and that's 0. So in that case, the horizontal asymptote is the x-axis, or y equals 0. If numerator and denominator have the same degree, then we know that the rational function has a finite non-zero limit given by the ratio of the coefficients of the highest degree terms. And so y equals that value is the horizontal asymptote. If the numerator has larger degree than the denominator, then we know that limits at infinity and negative infinity are infinite, so there are no horizontal asymptotes. But it turns out that if numerator has degree exactly one more than the denominator, there is a slant asymptote. And this is given by the quotient where you do long division. I will explain the reason for this using an example. That's a lot easier than trying to give a proof, and also easier to understand. If the degree of the numerator exceeds the degree of the denominator by 2 or more, then there will be no non-vertical asymptotic straight lines. Because when you compare the two, you end up with some number times x to a power that's bigger than 1, so it cannot be a straight line. We can talk about asymptotic parabolas and so on. That's not worth doing as much, so we won't worry about that. We will limit ourselves to asymptotic straight lines. Let's look at a couple of examples of finding asymptotes to rational functions. Again, to keep the algebra simple, we will look only at functions where numerator and denominator have fairly small degrees. The principles are the same no matter what the degrees are, so computations get longer and harder. So let's start by finding asymptotes to graph of y equals a rational function where numerator and denominator have the same degree. To find vertical asymptotes, first remember to reduce the fraction. So here I'm going to factor the numerator and the denominator. Numerator factors as 2x minus 3 times x minus 1. The denominator as 5x minus 3 times x minus 1. So x minus 1 is a factor common to both the numerator and the denominator, so we can reduce this fraction. The reduced fraction is not defined at 3 over 5. The denominator of the reduced fraction is 5x minus 3, that's 0 when x is 3 over 5. So that's the only vertical asymptote. X equals 1 is not a vertical asymptote because at x equals 1, the limit is a finite number. I will leave it to verify the limit is negative 1/2. So if you draw the graph of this, there is just a hole at the point 1, negative 1/2. There is no vertical asymptote there. What about non-vertical asymptotes? Well, the highest degree terms, it doesn't matter whether you use the original fraction or the reduced fraction. You should get the same answer at the end. If you use the original fraction, the highest degree terms are 2x squared and 5x squared. Or if you use the reduced fraction, it will be 2x and 5x. In either case, the ratio is 2 over 5. So that's the limit at both infinity and negative infinity. So that's a horizontal asymptote. There will be no slant asymptotes. This concludes our first look at finding asymptotes. Next time we will see how to find slant asymptotes.